Welcome to The Explainer. Today, we're diving into what is honestly an absolute masterclass in data analytics. We're looking at Sumit Saha's hackathon-winning project called the Default Rate Semantic Engine. Now, I want you to imagine working at a major fintech company, right? You've got this massive loan portfolio. We're talking real loans, real borrowers, and very real money. It's the end of the month, you ask your team leads for the portfolio's default rate, and what you get back is just absolute boardroom chaos. Let me show you exactly how this plays out.
First, you go ask the risk team, and they confidently come back with a default rate of 49%. Yep, nearly half the portfolio looks troubled to them. Now, why is that? Well, because their entire job is early warning. They use a super sensitive 30-day threshold, and they're only looking at the principal amount. They absolutely want to catch problems early so they can trigger collections. From their perspective, they would way rather flag 10 loans that eventually recover than miss a single one that actually goes bad.
But then you walk over to the finance team and they report a rate of 21%. Totally different story. You see, finance only really cares about the actual realized economic loss for the profit and loss statement. So they use a 90-day threshold, which is basically the point of no return where a loan is super unlikely to recover. And they also deduct any recovery amounts they've already managed to collect. It's just a completely different way to look at provisioning.
Meanwhile, you open up the board's report and they are staring down a massive, literally panic-inducing 72% default rate. But why is it so high? The board operates under a strictly conservative governance posture. They have this rigid rule that any restructured loan, even if the borrower is currently doing great and paying perfectly on time, always counts as defaulted because it just carries elevated risk. There are nearly 1,000 of these restructured loans sitting in the portfolio, so this one conservative rule makes their number absolutely explode.
And finally, the regulatory team files their paperwork and reports a 0% rate to the government. Zero. No way, right? Well, how does that happen? It turns out it happens simply because the specific government form they are required to fill out mandates a very specific origination cohort filter. Think something like all loans originated in exactly Q3 2024. If you don't specify a particular batch of loans for that box, the regulatory calculation just returns a 0 by design. So here is the central paradox of our whole data detective story. It's the exact same portfolio, the exact same loans, the exact same date. So who's right? How in the world can one single loan portfolio generate 4 vastly different numbers at the exact same time? Well, the crazy part is none of them are wrong, and nobody's lying. They are just answering entirely different business questions using the exact same label, default rate. Think about it. Risk is asking about early distress. Finance is asking about net credit loss. The board is asking for the most conservative worst-case view, and regulatory is literally just filling out a highly specific government form. The problem here is the word itself, and the fact that nobody had ever built an engine to actually reconcile all these completely different meanings. So let's look at the solution, which brings us to the semantic engine. And the word semantic here is key. It means the engine is actually dealing with the meaning of the information, not just the raw math. It uses a really strict 3-tier architecture that's specifically designed to reconcile all this chaos. And the best part? It does it without forcing a single team to modify their perfectly valid legacy calculations. We flow logically from raw data to conformed data to metric-ready inputs. Now, let's be real about Tier 1. Raw data, it is an absolute enterprise nightmare. This data is being dragged out of disconnected core banking, servicing, and collection systems that were simply never built to talk to each other. We are talking about 37 different spellings for just 7 canonical loan statuses. Current, cur, good standing. A naive system is going to treat all those as entirely different categories. You've got mixed date formats, conflicting Boolean flags, like some systems using y/n and others using 1/0, duplicate loan IDs, and even physically impossible negative principal balances. To fix this total mess, Tier 2 steps in and applies 9 strict business rules to scrub 2013 raw loans down into 1,953 conformed loans. And it does this through what engineers call an idempotent pipeline. That's a fancy but absolutely crucial technical term. It basically means you could run this pipeline 10 times in a row on the exact same input data, and you are going to get the exact same output every single time. And that consistency, that guarantees perfect regulatory auditability. Okay, so once the data is conformed, it moves along to Tier 3. Here, these newly minted metric-ready inputs are locked down as immutable objects.
Basically, they are completely frozen in Python and literally cannot be modified once they're created. Why is that such a game changer? Because it structurally prevents one team's legacy calculation, say a rogue script from finance, from accidentally modifying a shared loan object and quietly corrupting the data for everybody else.
So all of this infrastructure is leading up to one crucial point. We need a baseline. The engine establishes what's called the canonical rate. This is the single official golden number, and it was defined in a formal spec document before a single line of code was even written. The definition is crystal clear: 90 days past due, formally charged off, or in bankruptcy, period. And it uses gross exposure, meaning recovery amounts are explicitly not deducted. This canonical rate becomes the official anchor point. Everything else is measured against it.
But how do we explain the massive gaps between the teams? This is where the engine's reconciliation API comes in, and it is honestly fantastic. It takes those abstract, confusing rate gaps and breaks them down into plain English, perfectly auditable attributions. An old, clunky system would just throw an error or say, the board's rate is higher. Big deal, right? But the semantic engine, it tells you exactly why. It says the board's rate is 4,955 basis points higher because 957 restructured loans are classified differently. It literally names the cause. It turns an argument into something entirely actionable.
Now let's pivot for a second to the really rigorous engineering discipline that actually won this project, the hackathon. The creator totally bypassed standard happy path testing. You know, the kind where you just check if clean data works and call it a day. Yeah, they didn't do that. Instead, they used adversarial testing. They were actively trying to break their own system using extreme boundary testing. If a business rule says a default triggers at exactly 90 days, they didn't test day 50 or day 100. They tested exactly 89, 90, and 91 days to catch those sneaky, silent off-by-one errors.
And let me tell you, this was not just some academic exercise. The real-world stakes here are massive. One of the engine's 142 adversarial tests actually caught a real silent logic flaw. They ran a scenario where a loan was simultaneously restructured and charged off. The rules silently collided in the background, the code saw it was restructured, assumed it was performing, and just completely ignored the charge-off flag. Finding and fixing this caught a 127 basis point error, which literally saved the business from $655,000 in misclassified, silently excluded portfolio exposure.
Which brings us to a fascinating, quick micro lesson on how computers actually do math. In standard floating point arithmetic, which is what almost all computers use by default, 0.1 plus 0.2 does not equal 0.3. It actually equals 0.3 followed by a ton of zeros and a 4. Because computers store numbers in binary, a lot of simple decimal fractions just can't be represented exactly. And this tiny microscopic rounding error is exactly why default computer math fails spectacularly when you apply it to sensitive financial systems.
So to solve this, the semantic engine strictly mandates the use of Python's decimal type instead of standard floats. Sure, float is super fast, but it comes with those rounding errors and it's non-deterministic. When you start adding up millions of tiny errors across a $51.7 million portfolio, you end up with massive real-world money discrepancies just depending on the hardware you happen to be running it on. Python's decimal type might be a little slower, and it definitely requires more explicit coding, but it is exact and 100% reproducible down to the very last digit on any machine.
And honestly, it's this specific level of detail that totally blew away the hackathon judges. Reading straight from their honorable mention citation, they praised the project for showing a discipline that reflects genuine understanding of floating point error in financial systems, not just coverage for its own sake. It just completely validated their deep financial domain expertise. The engineer didn't just cobble together a tool, they anticipated exactly how real, messy financial data behaves at a massive scale. And if we zoom out for a second, you realize the semantic engine's architecture solves a universal corporate problem. Contested metrics happen absolutely everywhere. Think about revenue, right? Sales says you book it when the deal closes, but operations says it's only real when the product actually ships. Or headcount. HR counts full-time employees, operations counts physical desk seats, and payroll just counts the paychecks. This methodology, establishing a strict canonical definition while still preserving and reconciling all those legacy views, it works for far, far more than just fintech loans. So I want to leave you with this to think about. When it comes to how your own organization manages its contested truths, next time your teams walk into a meeting and fundamentally disagree on a core business number, ask yourself, are they actually arguing over the data or are they really just arguing over the definition?